before we get started, I have a couple of logistical announcements. So first of all, in light of our ever increasing COVID rates on campus, we're going to continue to hold class over Zoom next week as well. Hope they drop soon and hope you all stay safe. So that's announcement one. Announcement two is we are not going to have class on Monday due to Martin Luther King Jr. Day. So one more person admitting. So we won't have class. I encourage you all to use that time to do some sort of community service or to contribute positively to the world or society in the spirit of that day. And third, I also wanted to say something about my office hours. So I've noticed that not many people are signing up for my office hours. So I thought I'd give you some more information about like what my office hours are for. And this holds true for most faculty. But one way of using my office hours is a way, is you could use it as a way of like catching up or talking about the material from class, or like if you have course related concerns like accommodation requests, we can discuss those during my office hours too. So that I think you all know. But the other way to take advantage of my office hours is just like a way of checking in and talking. So I'm happy to talk with you about my lab's research or like help you brainstorm career plans or make connections for you or with you, or other stuff like that, even if it's not like immediately obvious how it relates to this course. So my office hours are for all of you, and it's just another way, in addition to our course meetings and email and Slack, for us to touch base and get to know each other. So there's no pressure to come to my office hours if you don't want to, or if you feel like you have too many meetings. And I totally get the am I wheeling on a unicycle? I am not currently riding a unicycle. Common misconception. Yeah, so I get the I don't know, Kareem, maybe that's...
We passed each other on the street.
My passed bad. Each other.
Yeah, I passed
that to go to
Alex
Alex
on the street.
And you were riding a unicycle.
Yeah.
Cool, right on. Well, that's exciting. Congratulations. Yeah, so I get the too many meetings thing, and Zoom meetings are terrible, et cetera, but I just want you to know that you have the option of taking advantage of that if you desire, and it's good to know about the opportunities you have, whether or not you decide to sign up. So there's a sign up link for my office hours in the syllabus that you can use throughout the term, and you can even sign up for meetings after the term ends if you want to discuss career stuff or anything after the course ends. So, all right. Again, no pressure. Any questions about any of those logistical things? No. Okay. So let's get back to the course content, our regularly scheduled program. So in module 1, which we are now done with, we focused on some approaches for telling stories in the general sense. And you all chose to focus on non-data stories. So hopefully the experience of putting together your own story and seeing how it was received by the class and seeing your classmates' approaches all helped you get some useful practice with the storytelling process. And we're going to keep building on that process as we continue in the course, and you're going to tell many more stories as we go. The shift that we're going to take moving forward in the course is towards stories that specifically include or are about data. So, the like major characters, plot points, illustrations, themes, and messaging, etc., are going to be driven by data and backed up by data. But just like there's no like right way to tell a narrative story, there's no one right way to tell a story about data. But also, just like we saw for this first assignment, different approaches and strategies might be differently effective at conveying particular data stories. So we'll also, but we'll also use many of the same ideas that you learned about in Module 1 when we're putting together data stories. For this next module, your main job is going to be to put together your first data story as part of assignment 2, which will be due next week, probably on Tuesday night. Actually, probably on Thursday night, now that I'm thinking about it. The way Module 2 is going to work is similarly to Module 1. So we're going to have some like discussions and lecture today. And then since there's no class on Monday, on Wednesday, we'll workshop your stories. And then on Friday and probably the following Monday, we'll critique each other's stories and get you some feedback. And then also, just like last week, there's no like coding required for your next assignment. We'll get to that later in the course. If you've taken a look at the assignment 2 instructions, you'll also see a lot of similarities between assignments 1 and 2. So the data story that you put together this coming week has to use data, but it can be about anything, and that includes something fictional. So you can like make up the data to better tell your story if that's what you like, if that's what you want. Also, this week, you can base your story off of one or more existing stories. But if you choose to do that, then you should retell the story in a new way or with a new interpretation. The key thing to focus on for this assignment, or the key things to focus on, are first of all, like how you can use data and data visualizations as effective narrative aids, and also how you can make your story interesting and meaningful while being constrained to focus on data, which can sometimes be boring or dry. Before class on Wednesday, you should take a look at the assignment instructions if you haven't done that already. And then I'd like you to come to class on Wednesday with some ideas for us to build on and workshop. Any questions? Oh, do we have X hour next week? We do not have X hour next week. Yeah, so it's literally just a missed class. Yep. Sorry. Or maybe you're welcome. I don't know, depending. Does anyone have any questions about assignment 2? Anna Marie and then Allison. Oh, sorry. How about Anna Marie, Allison, then Kareem?
Yeah, I just wanted to ask, I took a look at a few of the videos from the last year, and they didn't like necessarily, weren't like very heavy on like data visualizations, like maybe graphs, stuff like that. How like much of those should we include? Are there any kind of rules for that?
Yeah, so there are no hard and fast rules, but so pictures are a form of data. So you could have images to support your story. Since you're making it up, like hand-drawn things, you could pretend are photographs for this assignment. And then like graphs, you don't have to make a real graph, but you can either draw one, like sketch one out, or you could like find a graph that looks kind of like what you want on the internet. You could change the labels, et cetera. You can totally make it up. And sometimes effective data stories have like 1 million graphs. Sometimes they have just 1 or even 0. Anything's fine. It just has to be like, there has to be kind of a data-driven component to the story in order to fit with the spirit of this assignment. but that's very broadly construed.
Okay, thank you.
Allison, and then Corinne.
Yeah, I guess going off that question, so I guess there were a lot of varieties in terms of the like style, like some of them were more of a call to action or informative, some of them were more of an actual story. Is like one format preferred over another?
Nope, so that's part of the flexibility. So yeah, you can use calls to action to like inform your audience about a topic and maybe try to inspire them to take action. That's absolutely not required. You could just convey something interesting. You could even like convey something boring and try to make it interesting by like digging into it in a particular way, or like taking, you know, getting a new take on it. Yeah, but you know, this in the same way as assignment 1 was like pretty open-ended, this assignment is also quite open-ended.
And then I like in some of them, I thought like the presentation was really cool. So I don't know how to pronounce the person's last name. Like they were the one with the tigers. I think it's like Lenahan or something. I just like was wondering how they did that. I just thought the graphics were cool, or like if there are any tools you recommend for graphics.
Well, the easiest tools that kind of have the shallowest learning curves are like PowerPoint, Keynote. You know, you probably already have used these programs, or like Prezi. If like kind of the next level sorts of tools are like Illustrator, or like kind of the Adobe Suite animation tools. You could use iMovie. Personally, I'm not like an iMovie expert, so like I just use it to like splice video and like edit the, I guess, you know, I can blur stuff out and stuff like that, but that's kind of the limit to my iMovie expertise. But you could do something in iMovie, or yeah, any program is fine. And then, you know, when we get to the data visualization pieces, we'll like learn how to make figures without PowerPoint and Keynote and stuff like that. And so, you know, you can literally just screen share those figures if you want, or do something fancier. But like you could draw something on a piece of paper and like hold it up to the camera. That's fine. Yeah.
Okay, thank you.
Sure. I've always been curious about like in assignment 1, I like had a suggestion about like you could use sculpture, but like I've always thought it would be cool if someone did that. Like, could you make a graph out of clay or like food or something? Like imagine a movie about food where you use, or like anything where you use the thing to visualize it. That'd be pretty crazy, but not that you have to. Yeah. Kareem, did you have a question?
Yeah, I just wanted to know whether there was a limit of how many sources we could use to like compile a story.
You can, for any data story, you can never use more than 7 sources. This is a hard and fast, no, I'm totally joking. It doesn't matter. You could use, I mean, for this assignment, you can use 0 stories. You can just totally make it up. In general, you can use, you could use as many as you want. So yeah, yeah, and in general, you know, moving forward in the course, when you do real data stories, you know, you want to cite the source of your data set somewhere. It could be in your movie that you put together, or it could be in the documentation part of your assignment. So it's important to like give a sense of where your data come from. But, you know, the story pieces and the interpretation can come from you. And if it's your idea, you don't have to cite yourself. So yeah, it's kind of assumed that if you're the author, then you're coming up with some parts of the ideas. Yeah, Eliza.
Yeah, just a clarification. I got confused with the deadlines. So the deadline is on Sundays. What's on Wednesday?
Yeah, that's a great question. The reason it's confusing is because I've defined a deadline in multiple ways, and I'm sorry for that. So forget about the deadline posted on Canvas. I forgot about the no class on Monday and that everything would be shifted. And also when I posted the deadlines on Canvas, I assumed that we would take 1 day for going over the assignment 1 stories. So we're kind of shifted by 2 days. So assignment 2 is going to be due on Thursday at midnight so that we can discuss the stories in class on Friday. And then my guess based on assignment 1 is that we'll probably also discuss some of the stories on Monday. Yes, Allison.
So I assume then that for Friday, we should watch all the videos before class.
That'd be great. Yeah, so that's the reason I ask you to submit the assignments by midnight so that you can watch each other's videos that morning. Like, you're not going to get no credit if you hand it in late, but it just might, like, the later you hand it in or the closer to class, the less likely it is that your classmates will have seen your video. And often I have like meetings from early in the morning up until like the moment of class, and so if I can't watch it the night before, then I might not have time myself before class either. Yeah, but if life intervenes in your ability to submit the assignment the night before, like especially if we're spread over 2 days and it's sufficient, like a critical mass of students submit their stories so we can discuss on Friday, then like we could discuss your story on Monday, and I'm fine with that. Okay, cool. Okay, any other questions? Great. So I think I've mentioned before that I see the like storytelling part and the data part of storytelling with data as like partially separable. So now that we've gotten some practice with the storytelling part without being burdened by thinking about data, it's a good time for us to start adding in some of the data stuff. So mostly for this course, that's going to be about visualizing data in ways that help you to tell a story. So this week, we're going to be getting acquainted with data visualization. I should also note that, just like as a quick aside, another important aspect of the data part is, like in traditional data science, is carrying out statistical analyses and checks to back up your claims. And in this class, we're mostly going to ignore the statistics aspects of data storytelling. But if you've taken a stats course already, then you'll have gotten an introduction to like some of the key ideas. Here, we're basically going to be using visualizations as the key way of like finding underlying patterns without you having to explicitly remember anything you learned in your stats courses. But if you decide you want to use stats as we progress in the course, then first of all, you're welcome to do that. And I'm also happy to like help refresh your memory if and when that's useful, but it's not going to be strictly required. You should know though, in real world data science, so if you like go into data science as a career, then you're often going to need to do additional statistical analyses. And so, in a real data science role, then you need to synthesize what you learn in this course with what you learned in your stats courses. Before we dive fully into today's material, I want to take some time for us to get like in the proper mindset for thinking about data visualization. So as just like a thought exercise, I want you to start by thinking back to the visualizations you used in the stories that you and your classmates put together for your first assignment. So the story you just made. So do any of those visuals, either from your story or others, stand out as being like, first of all, memorable or particularly effective? And if so, why do you think that is or was? What do you think? Allison and then Emily.
So I guess a couple examples, I would say in Kareem's story, the use of the picture at the end where we couldn't see him was very effective because I think it was helpful in making his greater point, and it was nice in introducing humor and giving it a more personal touch. And then in Akia's story, I thought like the whole format looking like Yelp was pretty important to the story to kind of like set the context. So those are two examples I liked.
Cool, yeah, so both of those were kind of about context. So one is like the context in which you interpret a picture, which is like, something humorous. So that can help emphasize a point. And then the kind of immersive aspect of Akia's story with the like kind of vlogger interface sort of thing. That also, yeah, so that was a neat effect too. That's also kind of a contextualizing tool, like bringing the audience into the story and like inviting them to be a part of it. Cool, yeah, great observation. Emily, what did you notice, or what stands out for you?
I was gonna say I really liked in Alex and Fenry, the two like fictional stories and the illustrations they both did. I thought it was really great at bringing me into the world, especially because they were really detailed illustrations. So I thought that was something that was really effective in helping me picture what was going on. Plus, I feel like it's a lot of like hard work to draw really detailed illustrations and have them come out so well. So I was very impressed.
Yeah, so find like, details that are maybe hard to express with words, but there's the like picture is worth 1,000 words saying, but especially for abstract ideas or like things that aren't necessarily real or photographable. Oof, okay, I'm gonna work on my words today. Drawings or depictions or illustrations can be really helpful. And then if they're like visually themed or compelling, it can also help to like improve engagement. My cat wants to say something, but I don't understand. Sorry, I don't understand. Yeah.
Yeah. I remember you said like Alex, I forget you spelled like school and it had the word colon in it, like that kind of like level of detail. Like I didn't even notice it when I watched it the first time, and then I went back and I was like, oh wow, like this is really thoughtful.
Yeah, so also like the other thing that those details help convey is they help build your credibility as the storyteller, because it kind of shows that you are paying attention to the tiny details. So it conveys the sense to the audience that the storyteller is detail oriented. And so it's like, it's a kind of a hack for increasing your apparent expertise or believability. So, to the extent that you want that can sometimes be helpful too. Anything else that stood out that you want to bring up?
A couple of the images that I found most compelling are like bits of visual. We mentioned a couple of times the maps moving, or like the plane, and the movement there helped incorporate like a little bit more information into what would otherwise be kind of static. And in a similar-ish way, I remember the dog that was in Emily's story, like jumping, like that. The sense of movement, I think, did a lot for that particular visual.
Yeah, so Emily, I think in your story also, like the pictures were like you were playing around with the zoom, right? And like Yeah, that was a neat effect. I thought it also like helped kind of guide the eye and guide attention. So if you're like zooming in on something, then it feels like you're, feels like the act of paying attention to something or like focusing in on something in your everyday life. And so that can kind of feel natural. Cool. Yeah, so, oh, sorry, Cyril, yeah.
I also want to add on that, like all the drawings, I mean, obviously they're like for each of the video, like the drawings were drawn by one person, but like they're all very consistent, like all the drawings, like especially for Alex's, like all the like the facial expressions and all that, because they're very consistent. It was very easy to like follow the story. So yeah.
So that helped you like establish continuity and like having a consistent theme. Yeah. So in data visualizations, like, having a similar style across figures or plots or whatever, or like similar color schemes that, often something that's really effective is like the same color means the same thing across frames or images that can kind of help, convey information and guide focus. Yeah, these are all great observations, and keep thinking about that stuff. Obviously, this isn't an exhaustive list here. So part of what makes a good story, like a good story visual in the general sense, often also applies to the specific case of data stories. So like, you want to create figures that complement the narrative or convey a clear message in a compelling but memorable way, and like try to make them visually pleasing and consistent. But it's also worth thinking about like what some key differences between data-based illustrations and the sorts of illustrations used in last week's stories might be. So, maybe level, or well, maybe, does anyone have any thoughts about what might be different? Maybe I should ask you instead of telling. Like, do you see any difference or potential differences between like what might be effective in a data story versus like in a, story of the story you told last week? Yeah, Allison, are you raising your hands?
Yeah.
Okay.
So I guess a few things I would say for the data ones, it seems like the more simple it is, the better. And sometimes I guess like for the assignment one, like sometimes you wanted to make it more detailed to really bring the viewer in, but if you add so many details in the graphics, it make it kind of confusing. And also similarly, like less colors is more, whereas I'd say for assignment one, like colors can really also bring you into the story.
Yeah, so those are really great observations. So the thing that ties them together for me is like, how much is the viewer able to immerse themselves into your, like, how effective is the visual at drawing you in? So, with a like fictional story, like a fantasy story, or, I guess any story, doesn't have to be fictional. For stories of the story that you told in assignment one, like kind of visual detail can help transport you into the scene. But then it's not just level of detail. It's like, you can think of it like when I'm imagining what the image to go along with what you're saying, how much work does my brain have to do in order to like picture what's going on and understand what's going on? So the more detail that you provide as the storyteller, the easier it is for someone to be transported to your world. But in data storytelling, it's kind of the opposite effect. So again, the goal is like transport the viewer and make it easy for someone to digest. But like data visualizations are a little bit unnatural. Like we don't see data visualizations like walking around in our everyday life typically. And it's, it's certainly not how our brains evolved. And so you know, it's kind of a jarring, it can be a jarring experience to digest a complicated looking figure. And so you want to make it, like, again, lower the work required for someone, like, you know, for someone's brain to understand or digest or fill in the missing pieces. So simplicity is, you know, and just like mapping on what someone's seeing to other things they can easily interpret or understand, that'll kind of help transport too. Yeah, it's a really neat. Oh yeah, the other thing Allison was going to say is the refinement and credibility of the images. So yeah, so it could be, so you're saying it for data illustrations, who made the source, like who came up with the data or who generated the plot?
I guess I meant more like who generated the data. Like, I feel like, at least for me, like when I was watching some of the examples, when people didn't say like if the data was fake or where they got it from, I was like, is this really true? Where are you getting this information from? Whereas for the assignment one, if it's like my experience and I trust the narrator to tell it. So the credibility just comes to the fact that the narrator is telling it. Whereas for these, it's like, unless the narrator like is very established in the field or did the research themselves, then I would want to know where the source is coming from.
Yeah, I think that's a great point in general, that, you know, we want to like fact check and make sure our news sources and data sources are reliable. For this course, you're somewhat constrained by that because, you know, I guess, you know, we can all trust each other and whatnot, but you're not like established data scientists or news tellers or news sources. So, you know, there's that's a potential hurdle. But yeah, that's a good point. Yeah, so maybe like, you know, conveying that you're being careful or that you're just where you're getting the data is like reliable, that can help transfer trust from that data source to you. And then like kind of being careful about how you walk through the logic of what you're saying to make it transparent what you did and what you're saying, and give someone enough information to like follow along, but also draw the conclusions or come to the conclusions that you want them to come to. These can all be helpful. Yeah, Eliza.
Just to expand the point of Alison, I also think that if story, in the first story that we did, the data visualization part was too complex and rich, it would be also a negative point for the story, because at the end you don't focus your attention on the story itself, but you just fall inside maybe a too complex drawing, and you don't pay attention to the real story. You just got confused and
yeah, so you're saying like, is the visual complementary or like antagonistic with the narrative or the story? And you want it to be kind of complementing and making it easier for the story to be digested.
Yeah, kind of a complementary element and not a additional element that can make the story more complex, and make you just focus on what's important in the story and to follow the story better and not in a more complex way.
Yeah, totally. Yeah, so that kind of also falls into the realm of like kind of lowering working memory load for the viewer, and kind of how can you make it as easy as possible for the viewer to understand and follow along. Kareem, did you have a comment?
Yeah, it was. Can you hear me by any chance?
Yep.
It was more on one of the previous questions about how to visualize the data in our story. I think one really important thing is to not overcomplicate how the data looks. I remember I had a class this term where the first article we had to read was just a bunch of graphs, and no one really enjoyed it because the graphs were too hard to understand. So something that I learned in another class is that if the graphs quite complex, maybe write like a little sub-paragraph right there, just explaining what it is or the most important elements of it?
Yeah, sure. So text can be, maybe we're more used to digesting small snippets of text than complicated graphs. And so that, highlighting or, so either blocking out the stuff that someone shouldn't be focusing on, or zooming in, or adding little text boxes or something to help guide attention, that those can all be other ways of kind of reducing the burden on the audience. Yeah, so these are great. So yeah, keep thinking about this too. For the rest of today, I want to discuss and show you some strategies for, approaching how to visualize data. So I want to expand on the material that you reviewed or will review in module 2. And then I also want to emphasize some of the key concepts that I think are most important for you to take away. So there's a lot to take in. So I've put a slide presentation together to help make it a little bit more digestible. And let me also paste in a link to the slides so that you can skim through it as we're going, or you can review it later if you want. And then I will share my screen. All right. Can you all see my slides there? Okay. Sorry, I have to stop. I messed up. Okay.
Professor.
Yes.
How do you, I'm just not that familiar with GitHub. How do you download these slides?
Oh, can you I think if you just click them, they should be visible now.
They are visible, but if you want to download it, say as a PDF or in a PowerPoint format, can you do that?
Yeah, so it's a weird language that the slides are written in. So you can, there's one of the files in there. So if you change the .md to .html, then it'll look like a web page that you can click through.
Okay.
And it'll look more like the slide you're seeing here. I don't know what
Is there
presenter view does.
Sorry.
Yeah, I was wondering if there was a presenter view in PowerPoint, but it doesn't look like there is. So yeah. Oh, Alex.
Thank you, Alex.
Sure.
Made a PDF. Okay, cool. Thank you. Cool. All right. Okay, so I guess you could also take screenshots or whatnot, but that's a little annoying. Okay, so there's a lot to get through in these slides. I'm kind of just gonna power through and get through the full thing. Feel free to jump in with questions or comments. But if we go over time and you need to leave, then just do that. That's fine. And then I'll just put the rest on the recording, even if I'm the only one talking, and then you can catch the last part of the recording. Okay. So from one perspective, data sets are often pretty simple. So they're just collections of values like numbers and text and images and sounds. So in a sense, just printing out a table of those raw values is the most accurate way that we could depict the data. But that's also going to be a bad visual aid. So just one example, the complexity of many data sets comes from the fact that they are very large, and our brains are just not good at quickly processing vast tables of numbers. So here's an example of that. So on the right, I'm showing you like the pixel intensity values of a grayscale image. And at least for me, it's pretty difficult to interpret those numbers as any sort of meaningful pattern. But when you display the table as a visual image, like on the left, you can see that it's a low resolution image of a face. So the fundamental job of our visual system is to take in measurements of millions of tiny neurons in our retinas and interpret those numbers as meaningful patterns. And in everyday life, we rely on our visual systems and on our other sensory systems to guide our behaviors and make decisions and process and remember what's going on around us. But we can hack into our visual system's ability to quickly interpret vast amounts of information to also communicate insights about data. And conveying the patterns that we want people to perceive means figuring out how to turn data into pictures. Another important reason for like depicting data visually is that statistical summaries are often misleadingly impoverished. One classic example is called Anscombe's quartet. And this was devised by Francis Anscombe, who's an English statistician. So Anscombe's quartet is made up of the 4 data sets shown here in these scatter plots. So each point in each panel shows the X and Y values of a single data point from a single data set. Does that make sense? Okay. The surprising thing about these 4 data sets is that they appear very different when you plot them visually, but many of their statistical properties are identical. So all 4 data sets have the same mean X and Y values, the same variances for X and Y, the same correlations between X and Y, and the same best fitting regression lines. So if you were to summarize these data sets using the sorts of statistical tools that you might have learned about in your like introductory stats courses, then they would all look the same, or at least seem the same. A more recent version of Anscombe's quartet is called the Datasaurus Dozen. And it was created by Alberto Cairo. And you can see on the right that the mean and standard deviations of the X and Y values of all of these data sets and the correlations between X and Y within each data set are all preserved, even though the data sets look very different when we plot them on scatter plots. And another kind of neat feature of this animation is that those properties are even preserved during the warpings from one data set to the next. So, if you're convinced by these examples that visualizing data can be useful, we still need to think about like how we can turn raw data into a specific figure. There's no one right way to do this. It's kind of an art, but a useful way of like thinking through and defining what the options are is called the grammar of graphics. So the grammar of graphics conceptually is like a language for describing all possible figures that we could make, all possible figures that have been made or will be made in the future. And the fundamental idea is to kind of separate the pipeline that starts with the data and ends with a figure into a specific sequence of steps. So according to the grammar of graphics, each step in the data visualization pipe is called a layer. And each layer affects how the final figure looks, but it can work independently of the other layers. So the data layer defines the raw data set that you're going to visualize. The aesthetics layer defines which aspects of the raw data will be considered in subsequent steps of the visualization pipeline. So, you can imagine pretend our data set is a series of measurements taken from a fish swimming around in a fish tank. So like the raw data might be a table where each row is a set of 10 measurements taken at a particular point in time. And then like those measurements would each go into a different column. So you've got your like, maybe you could imagine them specifying the fish's like X, Y, and Z positions in the tank at each point in time. And like maybe it's yaw, pitch, and roll, and like other properties that, maybe reflect the fish's appearance or behavior at each moment. So if we were only concerned with the fish's movement through the tank, then we could define an aesthetic of the data set that discarded everything except the X, Y, Z positions. Or, we could do something fancier where we look at combinations of the columns in the original data set. And then the way to think about it is like anything not specified in the figure's aesthetic is going to get ignored in subsequent steps of the pipeline. Okay. Feel free to jump in with questions, by the way. This stuff is somewhat counterintuitive the first time. Okay.
Did you draw it out? I don't know if that's possible on here.
Like draw out what the aesthetics layered. So like I could draw out the fish tank example if you want.
That would be helpful.
Okay, sure. Let me let's see. All right. So like let's say, let me get color. Okay, so let's say we have like, our data set of fish. So each row of this table is going to be a time point. And then the columns are going to reflect different properties that we care about. Like, X, Y, Z, maybe the X, Y, Z positions in the tank. So, here's your fish tank, and here's the fish swimming around. Its position in the tank is going to be some XYZ coordinate. And then maybe like yaw, pitch, and roll, like, how is the fish kind of oriented along each axis, etc. So this might, in this, like what I'm drawing here, let's say there are like 6 properties of the fish that we're measuring at each moment in time. So here's like our first sample, here's our second sample, etc. Does that make sense? So this would be like our data set. And then we could define a data aesthetic to say, we don't care about yaw, pitch, and roll. We just care about the X, Y, and Z positions. So to do that, we would just ignore everything that's not in these columns. And that means that, even if the positions are the same between 2 time points, even if the yaw, pitch, and roll are different, then that particular time point is going to likely be visualized in the same way. Whereas, for some other aesthetic, like if we only care about pitch, then the X, Y, Z coordinates are not going to matter, and now only pitch is going to matter. Does that make sense?
Yeah, that's helpful. Thank you.
Sure. Okay. Okay, so that's data and aesthetics. The next layer is the geometries layer. And that's going to define a set of primitive shapes that we're going to use to represent the data. So like in a bar graph, the primitives might be rectangles, or in a line plot, the primitives might be lines, or like in a scatter plot, the primitives might be circles or squares, and so on. And then the primitives can also be complicated. So like if we're creating a map, a primitive shape might be defined by like the border of a state or a country. Okay. My son wants to contribute. Okay, but okay. Let's see. Okay, so that's like how we're converting the aesthetics to something we're going to draw on the screen, like shapes. Facets, the facets layer describes different subplots in the figure. So a subplot, you can think of just like a panel in a figure. So, and then each facet of the data set, or is going to go in a different subplot. So like the Anscombe's quartet figure that I showed a couple slides ago showed each of the 4 data sets in a different subplot. So for that figure, if the raw data was a set of XY coordinates, and then a label saying which of the 4 data sets it belonged to, the aesthetic would be the XY coordinates of each data point and the data set label. And then we could specify that the group labels should be used to specify different facets or subplots in the final figure. Okay. The statistics layer is used to specify like statistical models or summaries. So like if we wanted to have a regression line in a plot, then that would be specified in the statistics layer. And then for some types of plots like histograms or probability distributions, the statistics layer might compute the like mean or median of different data dimensions that are specified in the aesthetic layer. Or like the statistics layer might count up the number of times each unique value appears. It can also be really simple. So like the identity function would just take the data aesthetics that we specified and return the same values without changing them or computing anything. So like a scatter plot could be made with a identity function statistics layer. And then the coordinates layer specifies how to actually plot the coordinates in the data representation space that were specified in the aesthetics layer and potentially transformed by the statistics layer. So the coordinates layer is like saying, like if I'm trying to show this particular shape specified by the geometry layer, how do I actually display it on the screen? So we might want to show the data on like the Cartesian plane or in polar coordinates or on a geographic map or like any other map or coordinate system that we want to define. And that would be specified in the coordinates layer. And then finally, the last piece to a plot is called the theme layer. And that is kind of a catch-all that specifies all of the non-data elements of the figure, like axis labels and titles and color schemes and things like that. Okay. So yes, Allison.
So I guess like going back to the example you gave with the fish, could you, I guess, like, I don't know, draw a graph or something and like label where each of the layers would fall in?
Sure.
I don't know if these layers are more like how you're coding it, and so you can't really visualize them.
So, well, first of all, I'm happy to, we can go through the fish example if you'd like. So hold that thought for a sec. That might be helpful. But let me just say, like one more set of things about the grammar of graphics. So it's not actually critical that you understand like all of the details. So if you want to go through all of those ideas in detail, then I linked to 2 grammar of graphics papers in the module 2 material. So that like walks through several examples of like specifying different types of plots and that you might be familiar with using this language. And so that's a good exercise to go through. But you don't have to memorize these ideas, like, you know, and you don't necessarily even have to use them moving forward in this course. So what I like, the reason I dug into that and what I want you to take away is like the grammar of graphics provides an approach to thinking really systematically about like how to go about creating a figure or a set of figures to you know, visualize our data set. And then the you know, the expressive power of the grammar of graphics, like I said, it can encompass every visual figure we could make. So the expressive power is absolutely enormous. But by providing some structure to how we think about figures, the grammar of graphics can help us to make intentional design decisions and to understand the effects of those decisions. So later on in the course, when we get to, you know, working with different plotting toolboxes and libraries, you may choose to work with a toolbox that allows you to like specifically specify figures using the grammar of graphics. And if you decide to go that route, then it'll be good to like spend some time really understanding the different layers. Or you might also, or instead, decide just to like gain a more superficial understanding. And then, you know, just now you've been told about the grammar of graphics and you can like indirectly use it or have it in mind to like organize your thoughts. So that's how I'd recommend thinking about it. Okay. Akia, did you have a question or no? No. Okay. All right, so I'm gonna keep pushing forward. We could maybe go through the fish example at the end if you want. I'm happy to do that. But just in the interest of pushing forward. Okay, so to help guide your design process, you can start by thinking about like whether you want to display the raw values of your data set or a summary or both. And that might be determined in part by like how big and complicated your data set is, and also how readily the aspects of the data that you care about can be encompassed by summaries. Then you also want to think about like, are your, you know, observations discrete or continuous? So discrete data are things that take on like integer values like counts, or that can't have infinitely high precision like digital measurements. And then continuous values are usually analog, and they can like take on any real number or any real number within some range. I guess sometimes complex numbers too, but usually real numbers. Another way of thinking about the like discrete versus continuous distinction is about how samples are taken. So if you have like a set of unordered observations from each of several categories or individuals, then there might not be a natural progression across those observations. And so in that case, your observations would be discrete. But if you have ordered observations, like measurements taken at different time points, or like at systematically varying locations or something like that, then you might think of them as continuous. If your data are discrete, you might want to show that in a plot of the raw data by like keeping the individual data points categories visually separated. Or you could like denote continuous data by connecting the data points. A third consideration is to keep in mind is what patterns you ultimately want to explore or emphasize in your figure. So you'll want to pick a data visualization approach that has the potential to reveal those patterns. Otherwise, like you're never going to find them or convey them. And then the overarching goal that guides your figure design process is going to be like the message that you're trying to communicate. So you want to make your point as clearly and intuitively as you possibly can. Okay, so for the rest of our time, which is going to go over, but as I said, feel free to leave when you need to. I want to kind of bombard you with a bunch of examples of different types of figures. And I've organized them into broad categories, like whether the plots display raw numbers or summaries or what coordinate systems they use and whatnot. So, and then I've also chosen some examples of figures that like highlight particular types of patterns that you might find useful or interesting. So as I'm flipping through, I'll like say a little bit about each figure, and you should think about like which figures look interesting to you. And also like how you might be able to use them. So like what, think about what messages you could communicate with different types of figures. Another important factor in thinking about different figures is the wow factor. So some figures just look more visually appealing or interesting. So pay attention to which types of figures stand out for you or speak to you, or like which types of figures you find to be really intuitive. And those might be good things for you to use in your projects or stories. And you don't have to memorize these figures. You're all going to have access to this slideshow. I mean, you already have the link, and also you'll have the recording of today's meeting. And this is not a complete survey of all possible plot types, but I'm hoping it might like get you started thinking about different ways of visualizing the data. Okay. So the first group of plot types I want to show you is about displaying the raw data. So you've seen some of these figure types in the module 2 material. Maybe the simplest form of visualization is just a printout of the raw data set. It's called a table. It's the kind of rawest form of the data. A bar graph shows one number about each observation as a different bar, and then the heights of the bars reflect the values of those observations. So bar heights can be positive or negative, and the bar colors can be set to convey additional information or to help make the visual comparisons easier. And then bar graphs can also be displayed with the bars going vertically, like here, or horizontally. To facilitate comparisons between groups, you can use grouped bar plots. Each color here reflects a different group, and then the groups are separated along the x-axis according to some other dimension of the data. Stacked bar graphs are useful when you want to illustrate both the total values across groups and also the individual group contributions. Scatter plots map specific data dimensions or properties onto the XY plane. Or this is a 2D scatter plot. You just get the XY plane. You can use color and shape also to denote different categories or conditions in your data set. 3D scatter plots can highlight additional data dimensions or features. In practice, it can be hard sometimes to read 3D scatter plots, particularly if there's like too much going on, but they can sometimes be really useful, like in interactive or animated plots where you can like examine the figure from different views. In heat maps, you're converting each entry in a table into a color value. And a heat map can be used to display an image like a photograph, or any other sort of tabular data. A volume plot is like the 3D analog of a heat map. So each cube in the plot gets colored according to the value in a 3D table. These are used a lot in neuroscience applications, like to visualize the brain. Here I'm showing a volumetric brain plot on the left and then slices of the brain plot on the right. The next set of plot types I'll quickly review are aimed at creating summaries of the data rather than depicting individual data points. So one way of summarizing the data is to compute a bunch of statistical properties of your data set and then display them as a table. So it's not particularly visually pleasing or intuitive, but sometimes this format can be useful. personally, like I use these sorts of reports mainly as a debugging tool when I'm trying to like quickly compare different data sets or groups within a data set. But it's important to supplement them with other visualization approaches, like we saw with the Anscombe's quartet or data source dozen examples. Histograms display the number or sometimes the proportion of data points whose values fall within a particular range. And then it shows how the values are distributed in the data set. So visually, histograms look similar to bar plots, but the difference is that the x-axis positions carry information, and each bar in a histogram reflects data from a potentially different number of observations whose groups are determined by their values as opposed to some other label. And then a density plot is kind of related to a histogram. It looks like the darker blue curve in this figure. So it's like a histogram, but it uses a smoothing process to create a continuous smooth curve that approximates what proportion of the data took on each possible value along the x-axis. Histograms and density plots can also be shown in 2 dimensions like this. 2D histograms and density plots highlight how different dimensions of the data are related to each other. So for example, if you see like an oriented ellipse in the 2D histogram, it means that the 2 dimensions you're showing are like correlated or related to each other. And then in this example, you can also see 1-dimensional density plots on the top and right of the figure. And those can be useful for showing how the values along 1 dimension at a time are distributed. Ridge plots look really neat, kind of like a you want me to slow down? Sure, why not? I mean, really jump in with questions. I'm kind of just doing a survey here. But yeah, so like I said, you don't have to memorize these things. I'm just kind of flipping through, slightly slower than like flashcard speed. But if you have questions, jump in. Okay. Ridge plots, I think, look really neat. Kind of like a bunch of mountains receding into the background. So each row shows the density plot for some condition or data set. And then often the rows are ordered along some measurement dimension. So like you might use a ridge plot to show the distribution of some measurement varying over time. And then each row might be a different time point or range of time points. And then in this example, color is also used to distinguish the rows, and that can be a useful way of highlighting differences or providing a convenient way of referring to the rows. And then this example also labels each row with its own letter, but that's somewhat non-standard, but it's a possibility. Yeah, Allison.
I guess like I've never seen this before. Like, when would you use this?
Well, so the example I gave was like, if you have some process that's changing over time, you could like bin time into discrete bins and then plot the distribution of some of that measurement at that time point. So like, let's say you have you're studying like rodent navigation. So you have a rat running from one side of a maze or like a track to another side. Within some time point, you could plot the rat's locations, or sorry, within some time range, you could plot the distribution of like how much time the rat spent at each position along that track. And that would give you one distribution. And then you could visualize how the position changes over time by, plotting the succession of those distributions.
So I guess you're basically just combining multiple graphs into one graph in a sense. Because
well, it's kind of, yeah, so it's kind of like a set of density plots. So in that sense, it's combining multiple graphs. Yeah. Does that make sense?
Yeah, I guess because I was thinking like, could A itself be its own graph?
Yeah, of course.
Okay.
Yep. Yeah, so that would be like a density plot. Yep. Totally allowable. Yeah, you can also mix and match, your favorite parts of each of these types of graphs. And, that's a nice strategy. Let's see. So this figure shows a scatter plot, like you've seen before, which displays the raw data. But then the additional thing that's been added here shows the underlying trend in the data, or like how the X and Y coordinates are related. And that's called a regression line. So visually, regression lines can help to emphasize trends in the data. A vector field, or sometimes called a quiver plot, shows directional data. So at each point on a grid, the vector field plot summarizes the direction of movement for all data located at that point. And then in this example, the angles are indicated by the arrow directions, which are a little hard to see, but you can maybe see oriented lines, and then also by their colors and lengths. So vector fields are really nice for like summarizing any sorts of movement patterns, like currents or traffic flow patterns or migration patterns and that sort of thing.
Could you guys like use something else and like, I guess like what else, like say you were doing like migration patterns or traffic flow patterns, like what else could you, or is it typically vector fields, or do you use something else typically? I guess again, I haven't seen this one before either. It's cool looking, but I'm trying to figure out like when I would see it, or like when I may have seen it and didn't realize.
So if you ever watch the Weather Channel or like weather reports, vector field plots are often used to visualize like wind flow patterns. So you can imagine at each point on the surface of Earth or within some region of Earth, you might want to plot the direction and speed of the wind. And then, the nice thing is that if you zoom out, you can kind of see patterns, especially if nearby coordinates have similar wind directions, which is often the case because, wind is a continuous thing. You can see those patterns appear. The other related plot is called a streamline plot. So this is also used to visualize like currents and, including wind. So a streamline plot is similar to a vector field or quiver plot. But the way it works is if you imagine first drawing a vector field, each line in a streamline plot is drawn as a tangent to the angles in the vector field. So the lines kind of highlight the directions of movement within the coordinate space of the figure. So like if you imagine you're a fish swimming in a river whose currents are plotted by this stream plot, then if you end up on one of these lines, then the current is going to take you along the path indicated by that line.
So is this like a higher dimension of the vector field, if you will? Or like a zoomed
It
out
has
version of the
actually,
vector field?
it actually has the same information as the vector field. It's like, I guess if you picture like a, like contour plots in a, like on a map, have you ever seen those? Well,
I have to Google it, but
yeah. Or have you learned about like level curves in like calculus? Well, if you think of like, let's see, so if you picture a hill, like an overhead view of a hill, one way of visualizing the hill would be you color, like, let's say you're like, your view is like from a satellite camera looking down. So one way you could visualize what you're seeing, like the elevation pattern, is like, just plot each pixel in a color that like specifies how, like the elevation at that pixel. Another way to visualize, to like summarize that plot would be to say, let's take an elevation of like, 0 feet above sea level. And then you can draw a curve connecting all the points where the value is, where the elevation is 0 feet above sea level. And then you can take 10 feet above sea level and draw another curve connecting all the 10 feet above sea level points. So it's going to kind of look like a series of like almost nested rings, but the rings are going to look a little distorted according to like the hill shapes. So that's what a contour plot is. In a vector field plot, you're doing the same thing, but with like movement. And so now instead of like the elevation at each point, you've got some movement at each point, and then you're connecting like kind of the movement patterns, or the let's see, you're connecting the well, you're drawing tangent lines to the current directions, but you're like following the current stream at a set of like discrete locations, as opposed to just plotting the current direction at every single point. Does that make sense?
I mean, I think it's confusing, but I don't want to like go on it if other people understand what's going on.
It might help to Google like contour maps and like check out what I mean. I think you'll see the analogy, but like happy to dig into it further if it becomes relevant or if you want. Okay. So the next set of plots I want to highlight are combination plots. So they combine some elements of the plot that displayed the raw data and some elements of the plots that displayed summaries. And these sorts of plots are becoming increasingly popular in the scientific community because they're kind of viewed as more honest and open than showing only a summary. And then in practice, combination plots can often be useful, but they can also sometimes look visually cluttered, which can muddle your ability to effectively communicate. But they tend to be most effective when you have like just a few things to plot or compare. Violin plots are similar to bar plots or like box and whisker plots, but they show the full density plot for each condition or group. And then in addition, for each, in this example, the individual data points are shown as black dots. So you get to see both the like individual data points and also how they're distributed all in the same plot. So where the, curves are thicker, that means there are more data points with that value.
How is it different than like a box and whisker plot? I mean, this is cooler looking, but.
Well, a box and whisker plot doesn't show the full distribution. It just shows the like quartiles and then the outliers. So this is like a kind of a more or a higher resolution version of a box and whiskers plot. Swarm plots also show individual data points with each dot. And the swarm patterns are displayed in a way that indicates how the underlying distributions look. So if you have multiple observations at the same position, then in a swarm plot, the dots for those observations start to spread out from the middle. So if you imagine like dividing each color here into rows along the y-axis, then the wider the dots are spread out within each row, the more observations had that value. So it also like gives you a sense of the underlying distribution.
So could you explain like what this graph is showing? Maybe that would like help with understanding how the plot works.
Sure. So I think this is like a data set of like the tip amount that a set of restaurant workers received on different days of the week, Thursday, Friday, Saturday, Sunday. So each dot is one observation, so one meals tip. And all the tips from Thursdays in the data set are shown in blue. And then you can see that like several tips were in the like $10 to $11 range. And so those appear here. Whereas like there's only one, $44 tip. So that appears here.
So I guess with swarm plots and violin plots, they can show the same information. They're just different ways of showing the same thing.
Exactly. Yep.
Okay.
Yeah.
Is one like preferred over the other? Sorry, I didn't mean to cut you off.
No, it's just whatever looks better. Sometimes for, so you can show the individual data points here too, but then, if you have like a gazillion data points, then like violin plots can look nicer sometimes. If you have like, a gazillion points that you want to show and you have to show each data point, a swarm plot can look really messy. But the nice thing about a swarm plot is like, you could imagine an animation where like you zoom in on one of these dots and then show some other property of the data set for that dot. So that could be interesting. Or you could like highlight a subset of these dots and show something about it. Yeah, Lisa.
So are these graphs plotted with R or Stata? Where do they come from?
This particular plot is made using a package called Seaborn. We'll go over like data visualization techniques and packages and approaches as we move on in the course. So don't worry about how to make the plot, but just, you can see what looks nice. And then, you can always go back and flag some plot like, oh, I really want to know how to make that one. And then we can revisit it, but we'll learn about those tools. The first step is just to get a sense of like what's out there, because there are so many of them. So this is like a kind of modern take on box and whisker plots. This is called a boxen plot, or sometimes these are called letter value plots. And the idea is kind of like violin plots or swarm plots. So these are all like ways of visualizing the same sorts of things. But then each box within a group represents some range of standard deviations from the mean. And then the tops and bottoms of the boxes indicate the range of values within each group. And then the wider the boxes are along the x-axis, the more data points were observed with that range of values. Okay, but you can see these are, all showing the same sorts of things. Okay, here's kind of like the classic distribution plot. So box and whiskers plots, they're kind of the old way of showing this stuff. So they show the median, upper and lower quartile, the maximum and the minimum, and outliers, which are shown here as diamonds. And then like, the classic way to define outliers in box plots is like any data point that falls more than 1.5 times the interquartile range above or below the lower or upper quartiles. You don't have to think about that definition too hard. It's built into many of these packages. Yes, Allison.
This may sound like a dumb question, but I guess why isn't the outlier considered the max then?
Yeah, it's so if you assume your data set, your observations are distributed in some way, like through a normal distribution, then you could say if you have like a heavier than expected tail to that distribution, then under this view, which is not one I totally share, you could say these observations must not be real because, or I can't trust them because they fall outside of the, what would reasonably be expected if my observations were distributed in this way and the like mean and standard deviation was, whatever we observe. in practice, I think it's somewhat dangerous to exclude outliers. So I'm just showing the standard practice here. But like, you know, if you observe something, like, that's what it is. It's not like it's not real. But
So ideally you would say like, these outliers shouldn't be separated. The outliers should be the max, and like the whole thing is skewed, but that's the point, I guess.
so I'm, can you hear me? Can you hear me now? Okay. Sorry, my earphones just died. What was your question?
Oh, I was just saying like, oh, I think there's an echo, that's okay. I was just saying, ideally, like, if we were making this, would you just not include the outliers as diamonds, and the outliers would just be the max, and the whole thing is skewed, and like, that's just what it is?
Well, so this is how box and whisker plot is defined. So like, you know, that includes defining what outliers are. So there's a standard meaning to the boundaries of, you know, where these lines are drawn relative to the distribution. So I think, you know, that'll be built into, so this plot also is drawn using the Seaborn package. And, you know, the outliers are drawn and defined, you know, in standard ways. So I wouldn't change that per se, but you might choose not to use a box and whiskers plot and instead use like a violin plot, you know, which might be more in line with, you know, your view of the data set, or, you know, what you think is going on. Or a swarm plot also would show every data point.
Gotcha, okay. I guess, so maybe I just didn't realize, so you're saying the standard for box and whisker plots is that, well, so if the outliers are out there, did the outliers then affect the mean, or I'm sorry, the median then? Or
Yeah.
are the outliers not included in the effect of the median for
Well,
standard?
remember the median tries to be a little robust to outliers. So, you know, the lowest value and the highest value cancel out. And so if the distribution is skewed, the median is a little bit robust to that. So it somewhat tries to kind of fight back against heavy tails of a distribution. But the kind of more modern approach to visualizing distributions of data is to use like violin plots or swarm plots, or, you know, just visualizing the whole distribution like with density plots or histograms or something like that. Box and whisker plots are somewhat out of style, and box and plots are also somewhat out of style. But, you know, it's a classic way of visualizing data, so worth knowing about. Okay. A joint plot shows both the scatter plot of the data and also histograms and or density plots within each individual dimension. And then in this example, there's also a regression line that's added to illustrate the relation between the X and Y variables. There's a lot of stuff happening here, but, you know, it's another way to visualize data.
So I guess going off that, sorry for all the questions.
Yeah, no problem.
So how, again, so like what would this graph be telling us based on all these labels and like the two graphs? How would you interpret it?
Yeah, so this tells us, can you see my mouse pointer? So this tells us how do the X and Y values relate? And then how is X distributed? That's the top histogram and density plot. And how is Y distributed? How are the Y values distributed? And that's the right, or the histogram and density plot on the right. And then the regression line like shows the general trend in the like relation between X and Y here.
I guess another question I have is like, so when we're making these graphs, like, is our audience supposed to be the scientific community who's like heard of all of these, or should we like be mindful like using violin plots or swarm plots because people may have never seen before and not be able to interpret them?
So your audience for this class is it's like me and your classmates. So I think, but I mean, this is true for scientific papers also. Your audience might be the scientific community, but like scientists also like things to be easy to read and interpret. So if you think that, you know, a scatter plot is the clearest way to visualize your data set, then that's what you should use. If you think a violin plot is the clearest way, then that's what you should use. There's not like one plot type that's preferable in all circumstances. So the you know, the approach I recommend is like, you know, think about, you know, it's good to just like get exposure to many of the different options there are out there. And then you can think back to, you know, you'll have them in your mind and can like think about, oh yeah, once I saw this plot, it had like a scatter plot and some density plots. I think that would be useful here. And then you might not remember it's called a joint plot, but you know, you might be able to like recreate the key ideas or parts of it, or know like enough to search for it.
I guess people ever add like labels or certain descriptions? So, because I mean, once you explained the plot, it made a lot of sense. It's just like on first glance, it's a little confusing.
Yeah, so when you're telling a story with a plot, you can walk people through it. You can add extra labels. You're allowed, there are no real rules. So yeah, you can do anything. You can color one data point or set of data points you want to highlight. That's all totally fine. All right, another type of joint plot is kind of like the 2D histogram example that we saw earlier. So in this style of plot, each range of X and Y values is contained within a hexagon. And then the grid of hexagon tiles, there's like a grid of hexagon tiles across the XY plane. And then the colors in each hexagon tell us how many data points had values within that range of X and Y values. So the like two sides of the hexagons are the X limits, and then the top and bottom of the hexagons are the Y limits. And the reason they're hexagons is they like, you know, fit together, you know, well. You could also.
And what are the sides of the hexagons then? You said the top of the X limits, the bottom of the Y limits. What are the sides?
No. The sides are the X limits, and then the top and bottom are the Y limits.
Aren't there 6 sides?
So you can imagine drawing the whole thing as a rectangle, in which case so you could also draw, let's see if I, like a heat map would be an example of a 2D, you could use a heat map like thing to show a 2D histogram with square tiles. So let's see, so here, you know, there's like a set of data points that range in X value from here to here, but then this hexagon up here partially overlaps.
So I guess, can you pick out like a certain point from this and explain like how you get that? Because the rectangle only makes sense, that I just don't understand why there's 6 sides rather than just 4.
So the hexagon shape is just a way of packing them together. So it's like, yeah, Eliza.
Isn't just simply dots plotted in the graph, and then you kind of put together more dots that are inside the figure with 6, how is it called,
Hexagon?
hexagon, yeah. So in all the points that are inside the figure, then are associated to the color. And then
Sure, that's a good way of thinking about it. So yeah, so it's like if you have like a huge beehive shape, like a honeycomb shape, and you just like threw darts at the beehive and, I guess several darts could hit the same honeycomb and et cetera, then you could count up the number of darts that fell within each honeycomb square, and that determines the color. Honeycomb hexagon, and that would determine the color. Yeah, so actually, I think I misspoke. I think the borders of these hexagons probably are actually meaningful in that it's like any values that fall with, now that you're saying that, I'm remembering. I think it's that any values that fall within this border are counted in that count. In that hexagon, sorry.
So is it like, I don't know if this is true, but does a hexagon have a greater area or surface area than a rectangle? So they're trying to make it like, because at that point, why don't you just use circles or something even bigger?
So you could think about, what if you did use circles? There would be little spaces between the circles.
Okay,
So a hexagon is like circles that are squished together.
And then I guess are hexagons more commonly used than rectangles or squares in this case?
No, you could also use rectangles. It just, this is just called a hex plot. So it's another way of visualizing data. Oh yeah, and then the histograms, just like in the other joint plot, show how the data within each dimension are distributed. So you get, just like in the other joint plot, you get how the two dimensions are related. That's the hexagons part. And then how each dimension is distributed on its own, and that's the histograms. A pair grid is used to illustrate how each pair of dimensions in the data set are related. So in this example, the data set has 4 dimensions. So the plot has 4 subplot rows and 4 columns. And then the subplots along the diagonal show the histogram for each dimension individually. So like how each dimension individually is distributed. But then each off diagonal row and column shows a scatter plot of how those 2 dimensions are related. So like the first row, second column shows a scatter plot of the first dimension plotted against the second dimension.
These just like basically all of these could be separate graphs and you're basically just squishing it all into one graphic. I mean, or is there more to it than that?
Well, yeah, each separate, you could plot each of these as a separate graph, but the whole thing together gives you a sense of the full, like all of what's going on. So they're like related to each other. So the first row tells you how everything is related to the first dimension. So how's the first dimension distributed? How are the first and second dimensions related? How are the first and third dimensions related? And how are the first and fourth dimensions related? And then the second row tells you everything about the second dimension. So how are the second and first dimension related? How is the second dimension distributed? How are the second and third dimensions related? And how are the second and fourth dimensions related, etc. So yeah, you don't have to use this type of plot, but it can be useful for, understanding the full picture. It's not always useful. When you have multiple groups or conditions within the same with the same dimensions, you can create pair grids for each group and then show them on the same, show them all on the same figure. So you read this just like the pair grid, but now the colors reflect different groupings within the data set that we can compare now.
Wait, sorry. Can you go back for a second? So can you maybe, and is it possible you just to explain each of them or give an example of like how we'd see it for each of them? Just so I don't have to, because I feel like I keep cutting you off every time. Because I'll probably keep asking the same thing for most of them.
Sure. So I mean, this is the same type of plot as this, right? Except you can imagine that what's not shown here is that different data points have different labels besides just these dimensions that are being shown. So like, so I think this is, oh, these are like species of penguins, I think. And there's like different properties of each penguin. So bill length in millimeters, bill depth. I don't know what the difference between depth and length for a bill is on a penguin, but flipper length, body mass. So each color is a different species, and then each dot is a different penguin. And then you can plot, it's like bill depth as the y coordinate, or sorry, bill length as the y coordinate and bill depth as the x coordinate. And for Gen 2 penguins, those are all these green dots. Does that make sense?
So is the scatterplot matrix showing more like factors or dimensions than the pair one? Because that way you'd use this one over the other?
Yeah, so it's showing additional groupings within the data set. Oops.
So I guess like in other words, like.
So
like
this
it's-
data set and this data set, I'm pretty sure are the same.
Okay.
But here, so here it's like, you know, across all types of, all species of penguin,
Mm-hmm.
how do these measurements relate? So here each dot is just a penguin, regardless of species. But then you can separate out the distributions of each type of measurement and how they relate to each other separately for each species by showing them in different colors.
Okay, so it's just basically this is like adding another level of like, I guess, information, if you will. Okay, that's helpful.
Rain cloud plots are a relatively new type of figure. So they combine violin plots, these distributions, box and whisker plots right here, and also scatter plots all into one. So you get to see the raw data, a statistical, that's the dots, a statistical summary, those are the box plots, and then also the full distribution, which are the violin plots, and that's all in the same plot. And then in this example, we're also using color to denote different groups within the data set. And so like, you know, we can easily compare them.
I guess, how do you know this one is this like kind of looks different than a violin plot? I guess, do they not always look the same?
Well, the distribution is going to depend on the data set. So for every data set, the distribution might look different.
I guess like I thought the violin plot looked like, I mean, honestly, it kind of looked like a string bean and like there's just like a lot of little dots in it. But this looks more like,
yeah. So the dots in those other violin plots were the individual observations. So
Okay.
here those observations have been moved to the left. So two things.
oh,
So
okay.
there are a few things that have been changed. So first of all, if you look just at the distributions, those are like the right halves of vertically oriented violin plots. So it's like, you know, for each value along the y-axis, what proportion of observations had that value? And that's the kind of how far left each violin distribution goes. Then you've got the, you know, median, et cetera, all the, you know, statistical landmarks of, you know, shown by the box and whiskers plot. And then you've got the individual data points also.
So I guess the difference is it's just they're separating out the individual data points, whereas normally a violin plot, it would just be in it.
Well, technically a violin plot is just the distributions. In the
Oh.
example I showed, it also had the individual data points added in, but you don't need to show the individual data points.
I guess the other ones seemed more like contained like a bubble kind of, whereas this seems more just like a lot, like, I mean, a curve. I don't know. They just look very, I mean, unless I'm missing something, they just looked very different. Is it possible to go back to the violin plot slide?
Sure.
I guess it was just symmetric.
Yeah, I mean, these like, why are there, I mean, these are like actually contained figures. The other ones just look like normal curves on a graph.
Well, there, I mean, there's a black outline here, and the top and bottom are mirrored. But
Oh,
if you,
so that's not normal then? Or is that like an aesthetic thing?
no, that is normal for a violin plot. That's what a violin plot is.
Okay. So I guess in the other one, for some reason, they're not mirrored, or they're just not
Yeah,
outlined.
well, they contain the same information, like the top and bottom has the same information. So you don't need to mirror a violin plot, but you can.
So
That
then-
would be a density function, I guess. Like if you want to call it precisely with the name, it would just be a density function.
That's right. So the upper part of a violin plot would be just the, density curve for that, the distribution for that data set.
So then so I guess the other one, the rain cloud plot basically just doesn't have the bottom.
Yeah, so there are a few changes from that other figure. So one is just aesthetic. So there's no black outline, and only 1/2 of each distribution is shown. Like instead of mirroring each distribution, it's only shown once.
Okay.
Also, groups have been separated out into different colors. That's not critical for a rain cloud plot, but that's what's done here. And then in the violin plot example, this is not true of all violin plots, but like a violin plot just means you show the distribution and then you mirror it, and it's supposed to look vaguely like a violin, but in practice, I don't know, they don't look so much like violins to me, but that's what it's supposed to be.
Okay, that's helpful.
Yeah, and then so the data points now have been shifted to the left, so you can see them kind of off the plot, and then you're getting, it's supposed to look, or I'm assuming the name comes from looks kind of like a cloud. Like if you were to orient it, I guess flip it 90 degrees, you could this is kind of the cloud, and I don't know, maybe that's like lightning, and then there's raindrops falling out of the cloud. Okay. Yeah, so we have a few more. Okay, so next I'll show some polar plots, which plot circular data like angles or other periodic measurements. So the most common type of polar plot is the polar area chart, which is kind of like a circular version of a histogram. So the values are indicated by the angles of each wedge, and the amount that each wedge sticks out indicates how many data points had that range of values. And then in this example, the wedges are stacked, which shows how each of 3 groups contribute to the total. And a polar area chart is also sometimes called a coxcomb chart or a rose chart or a rose plot.
Sorry, wait, can you explain that one more time?
Say what it is.
Yeah, I was trying to take notes, but I only can type so fast.
Yeah, so think about wind direction. So you've got, at some point on Dartmouth's campus, over the course of a year, each day you could compute the average wind direction. So that's going to be an angle. Let's say the top is north, the bottom south, then you've got west to the left and east to the right.
Okay.
So this is like the kind of compass direction.
Mm-hmm.
Then you could say, well, if I often observe north blowing winds, then the wedge of this chart that's facing north is going to extend out further. And then if I hardly ever view west, I guess. west, west, north, west. You know, if I hardly ever observe this direction, then the wedge is gonna be kind of more towards the center.
Okay, so you said there's three parts of it. There's the angles, the amount it sticks out, and then whether or not they're stacked.
Well, the key parts of a rose plot are the angle and how far it sticks out. So you can think of it like the circular version of a histogram, but then you can
Okay.
also stack them. So here, the different colors reflect the contributions of three different groups. So you can imagine three different points on campus or something like that.
And sorry, what did you say was the related to the amount that the thing sticks out? What did you say that was again?
That's like how many data points had that range of values.
So it's like a frequency?
Yeah, it's like a proportion.
Okay.
All right. Pie charts are kind of the black sheep of the data visualization world, but they can sometimes be useful. So the area devoted to each color reflects what proportion of the data are in that color's condition. And then like the reason these are in, well, I'll tell you about the next plot and then I'll tell you why these types of plots aren't often used. So a target plot is similar to a pie chart, but now the areas are indicated by overlapping circles instead of non-overlapping wedges. So these types of plots are also in somewhat bad standing in the data visualization world. So in general, the reason is that pie charts and target plots kind of require judging the areas of circles, and people are just bad at that. And so they can be like confusing or misleading. Lisa, did you have a question?
No, I just wanted to say that I need to go, but at the same time, I wanted to talk to you, but I couldn't find the office hour and how to book them. So
Okay,
can I
it's
just
possible they were all booked up, but yeah, you can send me a Slack message or an email.
Okay. Okay, thanks. Okay.
Sure,
Have a nice weekend.
take care. Okay. All right.
Stuck with me now.
Yeah, all right. Okay, so well, I'm just gonna, even if you leave, I'll keep talking because I want to get through all this stuff.
No,
Okay.
I can stay. I don't have anything.
Okay, so clustering plots are designed to show groupings in the data. So like, you know, for example, between observations that have similar values or labels. So I'll show a couple of examples of how groupings can be illustrated. Oops. The most commonly used clustering plot is called a dendrogram. The idea is at the right are individual data points, and then the lines in the dendrogram group data points that are similar. And then as you move up the tree, the lines start to group similar subtrees. So, and then you can also use color to convey additional information or groupings. So like in this example, the colors denote the continents where the cities are located. But you've probably seen like a phylogenetic tree for biology, et cetera. So this is the type of plot that is. A cluster map is like a heat map that displays the raw data values. So each row of the heat map here is a different observation in the data set, and then the colors indicate the 4 values that make up each observation. And then the dendrogram on the top shows how the dimensions are grouped. So it shows like across observations, which dimensions values tend to go together. And then the dendrogram on the left indicates which observations go together. So it shows like which observations had similar sets of values. And then taken together, the cluster map is kind of like a joint dendrogram plot that shows 2 types of groupings at the same time.
How do they get certain colors? Like, is it based on like
These are just the
X values or
of the
something?
data. Yeah, these are just the values of the data set. So you can see the color bar here tells you how color maps onto value. It's a little bit small.
So it's arbitrary. It's not based on like, it's whatever you set the scale as. Like, I guess so what I'm trying to say is like, it's not like an RGB code or something and it's like,
No.
that number correlates. Okay.
No, yeah, so black means the lowest value, which looks like it's about 0.
Okay.
And then kind of whitish orange is 8, which is the highest value. And then you can see how like, red is 4, for example, or, reddish is 4. Okay. And then when you have measurements changing over time, the most common way to illustrate those changes, is called a line plot. So in a line plot, the x-axis indicates time and the y-axis indicates the measurement values. So in this example, you can see how 4 trends compare to each other by showing showing each trend in a different line color and line style.
Are the different, like the fact that it's dotted versus colored, is that just aesthetic, or is it significant that it does the fact that it's dotted?
It can convey meaning. In this example, it looks like it's just redundant with color. A similar looking type of plot is called a ribbon plot. And the main difference from a line plot is that if there's some like variability or uncertainty in the measurements, then you can indicate that by showing a thicker or thinner like ribbon around that time point. So like, yeah, you could show here like average activation relative to like showing something on the computer screen of like 2 different brain areas. And then if there's some variability over time in how those brain regions respond, then that's indicated by the ribbon thicknesses at the corresponding time points.
So it's the thickness from wherever the line is up.
Up and down.
Up and down, okay.
Yeah, and they don't have to be symmetric, but in this case, I believe they are. Yeah, so it shows, some confidence interval. So the, range where like 95% of the data live or something like that is a common one. Network plots are, if you want to illustrate something like a social network where people can be friends or communicate with each other, network plots can highlight connections between entities or data points. The simplest type of network plot is an undirected graph. Each data point, which can be something like a person, is shown as a dot. And then the dot positions and colors might reflect their values or like how the data points are clustered or grouped. And then the lines connecting the dots show which data points are connected. Undirected graphs like this can reveal things like community structure within a larger network. And then in like network speak, individual data points or network elements are called nodes. And then the connections between the nodes are called edges.
Wait, sorry. So wait, you said the node, can you explain what the difference are between the nodes and edges again?
Sure, the nodes are the dots and the edges are the lines. So the node is like an individual observation, like a person.
Yeah.
And then an edge shows a friendship relation, say, between 2 people.
Okay, and then are all the dots always going to be the same size, or is that something that also changes?
No, you can do whatever you want.
Well,
Yeah.
like, is that a thing?
Yeah, of course. Yeah,
Okay.
definitely. Yeah, so dot color, dot size, shape. Yeah, so you're allowed to do anything to, convey information. It's just a matter of what you think will be easy to digest. So there's a balance between like how many things you want to change. So the more differences convey information, the more information you can pack into a single plot, but which might be good because you get people to focus on less things. But then on the flip side, or like, you know, you get to make fewer plots. So you're like packing more information into a plot. So maybe that's easier to digest because they just get one kind of thing they have to look at. But then if they have to pay attention to many things and it's not super intuitive what they are, or like the pattern is messy, then you might want to show fewer things in the same plot. And so you kind of have to, you know, consider what message you want to show. A related type of plot is a directed graph. So that's similar to a undirected graph, but in a directed graph, the connections or edges are directional. So like in a conversation, person A could be talking to person B, but we might want to distinguish that from person B talking to person A. And then the connection arrows, or sorry, the connection directions are indicated by arrows on each line. Circos plots, which are also called chord diagrams, are a relatively new type of network plot that's becoming increasingly popular. In these plots, the network's nodes are arranged around the circumference of a circle, and then the ribbons connecting the entries show the edges. And then sometimes the ribbon thicknesses denote connection strengths, or like the number of connections between different groups.
Wait, sorry, can you go back for a second? Wait, so you said the network nodes, what did you say? Sorry about like,
Yeah,
so the ribbon thickness, the number of connections, you said something else. I missed it.
So this data set is like 10 different cities, or you know, roughly some number of cities in each of several different like geographic regions.
Okay.
So like continents or large chunks of continents.
And then, okay.
And then I can't remember what exactly this is showing, with like what is being plotted here, but you can imagine like shipping routes between two cities or something like that would show up as like, you know, the number of flights or shipping routes that connects these cities might be reflected in the line thickness that's connecting those two cities.
So what about the part that's like right very close to where the number part is, that's like very thick, that's not connected to anything? What is that?
Oh, those are just those just show the colors, the color labels.
Sorry, I didn't explain that well, but that's actually helpful to know too. I meant the part underneath it that's like lighter, but like not really, it doesn't like look like it's connected to anything.
Oh, this shows.
Yeah, like where your map, your cursor's now. Like, that doesn't look
Yeah, that's
like
a good question. I'm not totally sure why it's not connected. It might be like between all of these cities, or it might show some sort of directionality. I don't know.
Well, I guess it doesn't look like all the colors are connected to something else. Like some of it just looks like it's connected internally to stuff of its own color. Or it's just,
you know what? You know what I think it is? I think it's that the origin of the lines is connected to the like thick arc,
okay.
And then where it ends is shown in this as this arrow. So
that makes sense. Okay.
So like 0, 1, and 2 are connected to 7, 8, and 9, but it's going from 0, 1, 2 to 7, 8, 9. So you get a connection at 0, 1, 2, and then the arrow at 7, 8, 9. Whereas if you go from looks like 4, 5, 6 to a different continent, so it looks like Africa to Europe, 4, 5, 6 in Africa is connected to 6 in Europe, and so you get the green, like the kind of darker green, tealish coloring from Africa, and that's what determines the line color. And then you get an arrow terminating in Europe, even though it's lighter green.
Okay, that makes a lot more sense. Thanks.
The arrow notation is not common across Circos plots. It's just the common thing is just nodes arranged on the circumference of a circle, and then kind of arcs connecting the different nodes.
Okay. Sounds good.
Okay. A circular tree diagram is useful for visualizing networks that are organized as trees. So each dot is a network node, and then each line shows an edge. So the same as like the undirected graph. But if there's a tree structure, so if you think of like a phylogenetic tree, the most distant common ancestor, for all these animals in like arranged along the circumference would go in the middle. And then as you move away from the center, you can see how like different species branched off from their ancestors. So then the most recent species would be arranged around the circumference of the circle.
And then does it matter like where, like if it's a significant, like if it's like at the top, like north versus south, is that significant too?
You can add meaning to, you can have the position along the circle convey meaning, but so it's not like you can make any changes to any plot, but you don't have to.
So that's basically, that's not the standard. Like it's kind of where its place is kind of arbitrary, but it's more how far it is from the middle is what's most important.
Right.
Okay.
Okay. So just like colors can carry meaning in a scatter plot, the nodes in a network plot could also be colored to indicate some like important property that you want to highlight. And that's called a node color map.
And then is it based on gradient, I would think?
In this case, yeah, there's like maybe white is the lowest value and dark blue is the highest value, and then you fade,
Okay. And there'd be a key normally, right? So you would know what it means.
Yes.
Okay.
And then you can also color the edges of a network to convey meaning. So that would be called an edge color map.
Okay.
In an ego graph,
Looks like COVID.
kind of does. A node of like particular relevance or importance is shown at the center, and then its connections radiate outwards. It's like plucking one thing out of the tree and then you kind of hold it there.
Wait, so there's connections outwards, and there's connections among themselves too, I guess?
You can, yeah. I mean, you can have any structure to the network, but in an ego graph, you like highlight let's say you wanted to say something about this node in particular, then you could put it in the center.
And then what about all the other little blue ones?
Those are like the things it's connected to. So in this example, either never or almost never are the things that, or I should say, it looks like the things it's connected to are rarely connected to themselves, but
Okay.
That's not necessarily the case.
Okay.
Okay.
It's a funny name. The ego graph.
Yeah, well, it's like, like the
All about the $1.
yeah. Okay. Another widely used type of plot shows information projected onto the surface of the Earth, and that's mainly used to show location data. So the Earth is roughly spherical. So when we project the surface of the Earth onto a 2D figure, it necessarily gets distorted. And then different map projections make different decisions about like what spatial information to preserve versus distort when you flatten the surface onto the 2D plane. And most geospatial plotting tools support several map projection options. you've probably seen this sort of map before.
Yeah.
You divide up some part of the surface of the earth into parcels, and then you set each parcel's color to show how some value changes across different locations. So these maps are, commonly used to show like voting patterns or highlight patterns that are expected to vary by location. This is showing unemployment rate by county, probably.
Mhm.
A bubble map is kind of like a geospatial scatter plot. So each observation is tied to a specific geographic location and then projected onto the map. And then the sizes and colors of the markers can also be used to carry information. A geographical line plot is like the analog of a time series line plot, but they display spatial information instead of temporal information. So they're often used to show things like flight patterns or other movement patterns. And like you can use color to convey additional information too.
But you said that it was like the spatial, like you said it, sorry, it was like the spatial rather than like temporal information or something. So are you saying there's like a 2D version of it that's like the equivalent?
Well, you can show this in 2D or 3D. It doesn't matter. This is just one way of showing the world here.
Okay.
But as you move along these lines, what's changing is space, not time.
Oh, I see.
Like
Okay.
location on the earth. So you don't know, like if these are flights, you don't know how long the flight took or where it originated and that sort of thing. But you can follow the line and that's changing the location.
So, okay, so it's changing in location, not changing time.
Right.
Okay.
Animations are often like particularly visually compelling. So they allow us to focus on a subset of the total data set at one moment. And then they leverage our ability to synthesize information over time to communicate the full pattern. Pretty much any type of plot can be turned into an animation. Just like you can change the colors or sizes of different visual elements. In an animated figure, the individual frames of the animation are set up to distinguish some feature of the data. Just some examples. So Uber has put out some really amazing visualization tools and data sets. One example is this animation, which shows like commutes from different locations in New York City. Just a really neat looking.
It's cool looking.
Thing. Yeah. This is a famous animation that highlights how GDP and life expectancy are related. So each dot is a country, and then you can see how both GDP and life expectancy tend to increase over time as the animation progresses. And then you can also see when countries fail to carry that trend, when they like kind of visually drop out of the larger cloud.
So why are some of these dots much bigger than others?
I believe dot is population.
Okay, so we don't know which, I guess we can guess like based on how big they are, but it's really just based on like what continent on and I guess how big the country is, and then we kind of just guess which country.
Yeah, so in the source for this animation, you can even like roll your mouse over and it'll like label the country for you. So it's
Okay.
pretty nice animation. But yeah, or you could have text labels that move along with the dots. This animation is one of my lab's more popular visualizations. So the figure shows people's decoded thoughts as they're listening to a story. So each line is a different person. And then as the lines move through this space, it shows how people's thoughts change at different points in the story.
Does it tell you like, I mean, it's very cool looking, like, does it tell you like just showing that it's changing, or is it something more than that, or like the colors or something?
So each color is a different person. And then
Oh,
each coordinate in this space is like a different thought you could have. And then as you're
Okay.
listening to a story, it kind of drags your thoughts through some path. And that path is similar for different people, which is why it looks kind of like, you know, fish swimming together, eels swimming together or something. But then you can see like at particular parts of the story, everyone's thoughts deflect. And so those are kind of interesting parts of the story.
you said the color and the lines are the same person?
The color is like the person label. So
Sorry, yeah, and then same with the line, or the line something else?
which line?
Like, aren't they all individually like lines, or no? Are they just, or maybe they're not lines?
Yeah,
Okay.
it's the same color over time means the same person.
Okay.
Let's see. And then let's see, in addition to the sorts of like the standard sorts of plots, like the ones I've gone over so far, there are also a few like really classic plots that have had a big impact on data visualization that are worth knowing about. So you're probably familiar with the periodic table. So the periodic table arranges chemical elements by their atomic number and electron configuration and recurring chemical properties. And just like visualizing the elements in this way has transformed the study of chemistry. Charles Minard was a civil engineer who lived in the like 17 and 1800s. And he invented the concept of flow maps, and this is an example of flow map. And his most famous figure shows Napoleon's major losses during his 1812 Russian campaign. So the tan line shows the path into Russia, and then the black line shows the path back to France. The line's coordinates show geographic locations, and the thicknesses show how many troops are at that location at that moment in time. And then the time points are labeled along each path. And then the bottom panel also shows the temperature, which is expressed in degrees below zero at different time points. So the figure is like particularly neat because it succinctly represents 6 data types in 2 dimensions. So you've got number of troops, distance, temperature, latitude and longitude, direction of travel, and time, all in 2 dimensions. So it's also often like held up as an ideal data graphic because of how succinctly and intuitively a large amount of information is presented. 538's electoral vote depictions are also pretty neat. So 538 is a data science and stats blog that's best known for its like simulations to predict election outcomes. And this is from, this is one of their graphics used to illustrate potential outcomes of the 2020 election. So the winding snake depiction does a really nice job of indicating the predicted electoral vote breakdown by state. There are some common principles underlying the most effective data visualizations. One principle was articulated by Edward Tufte, who's like a famous data visualization guru. And the idea is to maximize what Tufte calls the data to ink ratio. The DINK ratio, not the DINK ratio. No, data to ink ratio, which you can think of as like the amount of information that each spot of ink conveys. So according to Tufte, maximizing the data to ink ratio will lead you to produce figures that are more intuitive because they force you to remove any extraneous detail that's not specifically conveying information. And then the principle also extends to like things that aren't necessarily ink per se, So for example, you should like minimize the unnecessary use of variations in color, size, shape, etc., that aren't directly improving the figure's ability to convey information. Like you don't want to be redundant in your changes. Whether or not you follow Tufte's principle, the most important thing to do is like whatever you can to make your figures intuitive and readable by your audience. Another consideration is how you use color. You can use color to intentionally highlight important data points or patterns, or to illustrate connections across figures. When you use multiple panels or multiple figure, or sorry, my brain's shutting down here. When you use multiple figures or panels within a figure, it's also useful to consider like how much visual weight each element takes up. So like, you know, how much is each figure or part of a figure drawing your attention? You want to pay attention to that. And then you want people's attention to be drawn most to the most important parts of your visualizations. And then the kind of last rule is the lack of rules. So none of the figure styles or principles that I've mentioned are like hard and fast rules. So you should use the ideas we've talked about today to help guide your design process, but you can break any rule if it allows you to communicate more effectively. All right, so that's data visualization. So just to remind people viewing this as a recording, please take a look at assignment 2 and come to class on Wednesday prepared with some ideas for that assignment so that we can workshop them. See you all on Wednesday.